Hello and welcome. If you're watching this video, I'm assuming that you've already read the chapters on intermolecular forces and solids, liquids, and gases, and that you've already watched the videos on D2L, taken notes from the PowerPoint, and now I'm just going to give you a little bit of practice. So I would suggest that you get a paper, pencil, eraser, calculator, periodic table that shows electronegativity values, and let's get started. All right, so the first question, can you draw a Lewis structure for sulfur dioxide? So go through the steps. What's the formula? How many valence electrons? Central atom. And this is a great time to pause the video and practice that. All right, how did you do? Did you figure out sulfur dioxide is SO2 and that there are 18 valence electrons? Did you put sulfur in the center with oxygens on both sides? Well, as you put in those bonds between sulfur and oxygen, did you subtract the 4 valence electrons so that there are 14 left? And then did you put those other remaining 14 electrons around the surrounding atoms to start with? Mine were around there originally. There we go, 2, 4, 6. I believe that electron right here on sulfur should be down here with oxygen. So that's 2, 4, 6, 8, 10, 12. So I have one more pair of valence electrons to put around. And I'm going to put those on sulfur. And now I'm going to count up to see if everybody has an octet. Sulfur has 2, 4, 6 electrons. Oxygen 2, 4, 6, 8. If I counted that, 2, 4, 6, 8. So our sulfur does not have an octet, and we're out of electrons. So what do? We're going to take one of these pairs and take them away from here and make a double bond right here. Now, everybody thinks they have an octet. And so that is what we do there. All right, now, taking a look at that, our electronegativity values, a difference of 1.1. So this bond is polar. So what that means is oxygen is a little bit more electronegative. So that means oxygen is going to pull these electrons toward itself, and it's going to become a little bit negative. Now, let's take a look at this molecule. Does this molecule, the shape of this molecule, allow one end to be negative and the other end to be positive? And the answer is yes. So it is also a polar molecule. Now, what is going to happen with these polar molecules? They're going to be kind of like this. There's our double bond there. That double bond will, actually, we don't even need to worry about what that double bond will do. And they're a little bit negative, a little bit positive on the sulfur, and a little bit negative on the oxygen. All right, and so if I have a bunch of these SO2 molecules, like if I had them sitting together in a bottle, in a pipette, what's going to happen is there is going to be an attraction between the positive end of that sulfur and the negative end of the oxygen. There's going to be an attraction here as well. And here, there's going to be that attraction. Those oxygens are going to repel each other. And that, because sulfur dioxide is a polar molecule and there is an attraction between them, that attraction is called an intermolecular force. And that's what we're going to be taking a look at. All right, so taking a look at water. Water is our most famous polar molecule. And so here the forces are already drawn for you. Generally, these intermolecular forces are drawn with dashed lines. So that is our intermolecular force, also known as van der Waals forces. So what's shown with that solid line? What have we been showing? That, hopefully you're thinking, is our intramolecular force. That is our covalent bond. And so you do need to know the difference between those two words. So there are 4 types of intermolecular forces you need to know. Really only 3: hydrogen bonding, dipole-dipole, and London dispersion forces. So if we have this molecule and we had other molecules, either the same molecule or different molecules, would they stick together? Would there be some kind of cohesion or adhesion between them that allows them to stick together? Now, the basis of what would allow them to stick together is what we would call electrostatics, electrostatic attraction, because there are opposite charges of the molecule. And these intermolecular forces, don't get them confused with intramolecular forces. Think about an interstate highway like 113. You can hop on 113 there in Georgetown and head south, and you'll cross over to Maryland. It's still 113. That is an intermolecular or an interstate highway. It goes between multiple states and stays the same. These forces go between multiple molecules, and it's the same force. It's an intermolecular force. If you played Deltec softball and you played other schools, you'd be playing intercollegiate athletics. If you played intramurals within Deltec, that would be intramurals. All right, so again, three main types that you need to know. London, dipole-dipole, hydrogen bonding. Now, a lot of people get concerned with this term dipole-dipole. Don't be confused or concerned about it. Dipole, take the word apart. Di means two, pole means two poles. So if we take a look at this molecule right here, this here's one pole, it's negative. Here's the other pole, it's positive. And so that's all that force is saying. All right, and so if we look at them from strongest to weakest, covalent bonds, of course, which are only really intramolecular force, are the strongest, followed by ionic bonds, hydrogen bonding, which is an intermolecular force, dipole-dipole, and then our weakest force is London. Now, London dispersion forces are very dependent on the size of the molecule, and that is very important. You need to know that. All right, so what type of force would this be, holding these two ions together? Hopefully you were thinking, oh, well, that's an ionic bond. Those are ion-ion forces. I know it's an ionic bond because sodium is a metal. All right, so let me just tell you a little bit about each of these forces. The first one, we're going to start with the weakest force, dispersion forces, sometimes called London dispersion forces. And this force exists between all molecules. It occurs because the electrons are constantly moving. And that's why in larger molecules, this intermolecular force, this London dispersion force, would be stronger. All right, so let's do a dichloride molecule. Take a moment and draw that. Figure out its polarity. All right, what did you say? Did you say, oh, well, that's got to be Cl2. I know Cl is diatomic anyway. It's going to basically look like this. It's going to be linear in shape. Our electronegativity is going to be the same, because the electronegativity of chlorine, I don't even need to look it up, is the same as the electronegativity of this chlorine. So is either of these atoms pulling on the electrons more? No. So there are no charges. So this is a nonpolar molecule. So if we looked at it like this is what the molecule would look like. Now keep in mind, in this molecule, the electrons are constantly moving. And so I could come over here and bring a big negative, ugly meanie, and that may scare the electrons, right? And so if I could scare the electrons to opposite sides of the molecule, I would get something like this. Now, how long is this polar molecule going to last? Only a short amount of time, and it's going to go right back to where it was, that nonpolar molecule. And so if there was any attraction between these molecules, it would be London dispersion. London dispersion is always the intermolecular force between nonpolar molecules. So once you figure out if a molecule is polar, then you could figure out that it would be London dispersion. Now, for a larger molecule, we're going to have stronger forces, and that's because there's a greater space for the electrons to move to one end. So imagine this molecule was this big, and that plus sign is way over here. right? So there would be more opportunity for those electrons. All right, the next one I wanted to tell you, so that's what happens. So if the chlorine on the right, if the electrons in there moved to the right side, and this right side would be partially negative, this left side would be partially positive, the electrons in the other molecule would also move for a charge separation. All right, so that's London dispersion force, an induced dipole. We're going to have to cause this to happen. All right, the next force I wanted to tell you about is dipole-dipole. This is whenever you have a polar molecule. Again, that word, dipole, two poles, like HCl. Anytime you have a molecule that has a negative end and a positive end, the force of attraction between these molecules is going to be called a dipole. It's really just that, whoops, sorry, this should be negative, not positive. It's really just that simple. The third force you need to be aware of, the third intermolecular, I was going to tell you a little bit more about dipole-dipole first. So again, these are polar molecules. There is a natural attraction between them. These are weaker than ion-ion forces. This is not completely negative. That's why we have to use that squiggle. It's like about negative 0.3. All right, the next one I want to tell you about is hydrogen bonding. This is the strongest intermolecular force. Actually, when they discovered it, they thought it was a real bond, like a covalent bond or an ionic bond. And then they learned that there was no exchange of electrons. This exists whenever hydrogen is directly bonded to oxygen, nitrogen, or fluorine. So I like to think ET, phone home. Phone home, fluorine, oxygen, nitrogen. Again, they're not real bonds. They're just extra strong attractions. And so you, as you're drawing the structure, you have to look, is hydrogen bonded directly to nitrogen? Is hydrogen bonded directly to oxygen? Is hydrogen bonded directly to fluorine? To figure out if it is a hydrogen bond. We see this in our DNA. This is what holds our DNA strands together. All right, so let's do some practice. What type of force would you say this one is? Hopefully you said dipole-dipole. I can see hydrogen is not directly bonded to F, O, or N, so it couldn't be a hydrogen bond. It is a polar molecule, so it could not be a London dispersion. All right, just a little about, all right, what type of force would this be? Hopefully you were thinking that's an ion-ion force. Magnesium is a metal. It's going to give away 2 electrons. Again, the greater the charge, the closer the distance, the stronger the attraction, just so you know. Remember, electrostatics is the basis of all of these. How about this force? This is an ion dipole force because we have an ion here, and this is a polar molecule, a dipole. And often these polar molecules are shown like this. What about this one? Hopefully you were thinking that, well, that's an ion on the right, that positive ion, and we're going to have a London dispersion or an induced dipole force right there. How about this one? This is a dipole induced force right here. All right, here's an opportunity for you to practice some on your own. Take a moment, pause the video, and figure each of these out. Will you need to draw these? Yes, many times you will. All right, so what did you say? CF4, London dispersion. NH3, because hydrogen is directly bonded to nitrogen. Remember ET phone home? Ne is just a London dispersion. Now, Ne is a pretty small atom, so if it were larger, the London dispersion force would be stronger. And then dipole, dipole, and then put them in order from strongest to weakest. Ne has the weakest force because it is smaller than CF4. CF4, of course, would be a tetrahedral shaped molecule. All right. So where do these intermolecular forces come into play? Well, here's where they come into play. Determining whether something is a solid, a liquid, or a gas. Because there has to be a balance between temperature and intermolecular forces. I would suggest that you kind of take a look at this PhET simulation. It is linked right here. I can also send you that simulation so that you can kind of play around with solids and liquids and gases. And so something turns from a solid to a liquid to a gas when temperature or pressure is varied and a change in energy occurs so that the molecules or the particles that make them up are moving more or less. And so these are all words that you're going to need to know. Sublimation, deposition, condensation, evaporation, melting, and freezing. I'm sure you know melting and freezing. You wouldn't believe how many people get that incorrect on a test when I say solid ice turns to a liquid and they said something else. It's sublimation and deposition that may be difficult. You may remember the day I showed you some dry ice. It turns directly from a solid to a gas. That would be sublimation. When that gas turns back to a solid, that's called deposition. And so here's just a little picture of solids, liquids, and gases. I know you already know what these look like. You can see the reason these are solids is because their kinetic energy is much smaller than their intermolecular forces. The intermolecular forces here are stronger and holds that solid in place. Of course, gases on the opposite spectrum, their particles have much more kinetic energy, are moving much faster than the intermolecular force. So essentially, gases have very little intermolecular forces between their particles. And so a couple things you should just be aware of for the properties of solids, that they do have a definite volume. You can't really change them. Gases and liquids have a definite volume and gases do not. We can compress gases, as we'll see next week in the lab. And then you should just have an idea of some of the different types of solids. Molecular solids, like glucose. You can see this is all a covalent bond, so these would be the intermolecular force between them would be weak, and that's why glucose or sugar is like kind of soft, you could say. So that would be a molecular solid again because it's all nonmetals. It is covalent bonds joining them together. Ionic solids are brittle. They generally have this arrangement, which I know you've seen before. So when we hit them, they often break. This is also why they have high melting points. And this is a great model of metals. This is kind of like if you have a sheet of aluminum, people may ask, how is it that I can have just a sheet of aluminum? Well, it's because the nuclei of these metals, atoms, don't care to hold on to their electrons. That's why they're good conductors of both heat and electricity. And here's a covalent solid. Again, high melting points because of this arrangement, extremely hard. This would be a network covalent solid if you had diamond. So if that would mean that each of these atoms was a carbon atom. And so here's just a little summary for you so you can see the kind of forces between them. Keep in mind that our molecular solids have these intermolecular forces. Could be dipole-dipole, London dispersion, or hydrogen bonding. And that is what I have for you today. I hope this helps you as you're working through Unit 3.